Now the next step is I want to use this signal block diagram to analyze a situation with given values. The situation should be the following. I start this system with original height y0, h is 0. Starting point is, also initial value is 0. And then I switch on an outlet flow with given value, and I want to calculate the reaction of h. What happens if I have a switch on of a constant output flow with h? Is this system able to pull the level of the tank back to the original value or not? That is an analyzing question. In mathematical words, we want to have the step response. If here's a step function QA, we want to have the step response of h. That can be easily done with a simulation program. And the simulation program needs some concrete values. So I give you some concrete values, and then I show you how to use my simulation program Regc, a freeware program you can find in Toolprogramme, Wireline, in the Moodle course, or on my homepage. And you can easily start this. I will show you how to do this. But first, simulation program needs numbers. So first I start with numbers. The area A should be 1 square meter. The original height should be 1 meter. So you see, starting volume is 1 cubic meter, or because we also have the volume dimension liter, 1 cubic meter are 1000 liters. Okay, that's the first thing. So you see that's a big tank. 1 square meter is like a rain ton, rain tank. 1 square meter is 1000 liter here. Now I switch on QA. QA step from 0 to 100 liter per minute. So what happens if we switch on this consumption, this suction, 100 liter per minute, 1000 liter tank, so the tank is empty in 10 minutes. So this is a situation without controller, but now the controller will work. If the swimmer goes down, here we open an input flow QE, and this will stop the decreasing of the level at some point in some mechanism, and I want to see how this level drop will stop, or what is this for a curve for h. The curve for h I want to have. But we need some values more. A is clear, QA is given. We need a value for C. C should be a valve constant, which gives, C is a ratio of, if I multiply with the size of the movement of this connection, multiplied with Z gives a flow which fills water into the tank. I want to do this in the following way. C should be 10 liter per minute if we have 1 centimeter change of the connection to the lever. If this is 1 centimeter, we have 10 liter, 2 centimeters, we have 20 liter, and so on. So this is a linear ratio. 10 centimeter, 100 liter per minute. Yeah, so this is the ratio, and LZ should be 0.5 meter and LH is 1 meter. So simple numbers, simple units. The only thing what we have to do is in our program, of course, we have to decide in program. Time base is minute, 1 minute, and the distance base is 1 minute. Sorry, 1 minute. Distance base is in meter. I want to have all lengths in meter. Then just I can delete, or yeah, I can ignore the units. But liters and meters are different. 1 liter is you see 1 divided by 1000 cubic meters. So if I have 100 liter per minute QA, I need the conversion into meters. This is 0.1 cubic meter per minute. And C is 0.01 cubic meter per minute divided by 1 centimeter, and 1 centimeter is 0.01 meter. And you see cubic meter, sorry. Here you can delete 1 meter, and we have here square meter in the top. So we have finally 1 square meter divided by minute. And if my program has a time is 1 minute and the distance base 1 meter, C is 1, A is 1, LZ over LH is 0.5, and then we have, and QA is 0.1. Then, and H is then in meter. The output comes in meter. Okay, so with these numbers, we can, before we start to simulate, we can guess the result. So that's a good way if we use simulation programs, that we know what we expect as a result of a program. Then we can easily detect errors, or typing errors, or number errors, or what you want. Yeah. This step response, we call it the step response. Yeah? The response of a step is a step response of this 0.1 square meter without controller. Let's do this in red. Without controller was this curve. This is 1 meter. And we know if I have no controller, we reach the 1 meter level, so the tank is empty after 10 minutes. Now if we have 100 liter per minute output flow, then 1000 liters are gone after 10 minutes. Okay, in green, what happens with the controlled output? Of course, in the first moment, I have the same situation. The level goes down. But the more the level goes down, the more the valve opens and it refills the tank. So we expect a curve, which goes this way. And if we look deeper to the mechanical system, we can find out the following. There will be a constant level of this tank. There will be a situation where all changes come to an end and all values stay at a constant value. That is the case if QA and QE are the same. Yeah, if we have the same input flow as output flow, then the change of H comes to an end. If you have 100 liter here, and we want to know the here steady state, the final value, then this is the case if QE is 100 liter per minute. We get 100 liter per minute if this is 10 centimeters, and with the lever law we get this if h is 20 centimeters. So we know, very simple, the final value of my system must be at a value of 0.2 meter. Steady state final value. Steady state. Yeah, I think you can follow this. But I guess the size of the curve is unknown. You can get the size of the curve, the function of the curve, with solving of a differential equation or using our simulation program. So now I go into Regc Sharp. In a video I have presented an introduction. In a 28-minute video you can see some function of this, so I assume that you have seen this video, have found the position of Regc Sharp. Maybe I should do this again. I show you in Moodle course where you can find the Regc Sharp program. So if I click on my dashboard, you have to look for the Toolprogramme Bayerline. That is in the course Studiengang übergreifende Kurse EI, also in SG übergreifende Kurse, Toolprogramme Bayerline. If you go there, go down to the point Regc Sharp. Here this is a presentation and demonstration program, and you need just the Regc Sharp run this file, unpack it, and then you have an executable. Just click on the executable and then the program will start. Yeah, this is a way to just run with my simulation program. If I do this, I have of course have done this download. In my case, we have just click on my Regc Sharp button and then the program will start. I just adapt the size a little bit, shift into my recording window, so, and you see this program opens with German menu points. In our case, of course, we want to have English menu points, so there is a button where you can switch between German and English only one time. It's no way back to German language, then you have to restart the program. But if I click one time on this, then we have the English menu points. Here you have some blocks you can put on your area of the signal block diagram. And here with this button you can draw branches, here summing points, and here add minus signs to branches. In our case, we are very simple. Now 3 blocks. Yeah, we reopen our system. We want to put in this signal block diagram. We have here a summing point. If I delete the summing point, yeah, we don't need the summing point. I need this summing point. I have this is a P controller, P actuator, and an integrating process. So I need a P block, a second P block, and an integrating process. Here the first P block has a gain constant 0.5 divided by 1, so 0.5. Yeah, I start with a P block. P blocks are drawn in this way with this symbol. We will talk about this symbol later in this lecture in more detail. And the block gain of my lever is 0.5. Say OK. I need a second block for my actuator. I put it here and the block gain is 1. C is 1 meter square meter over a minute, so this is unitless in this program. The size is 1. Say OK. Then followed by a summing point. I put here. Adding now an integrator. This is an integrator block. Putting here, and the constant here, the block gain K, is negative 1 over A. A is 1 square meter, 1 over 1 is 1. With -1 we have the negative sign implemented in my program, so I just type in a -1, say OK, and now we need only branches. Branches are drawn with this W button, and the drawing of a branch needs 2 clicks. The first click is the starting point. Let's start here. The first click. The second click is the ending point of the branch. Start, end. Now click, 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 click. So I make for each branch 2 clicks, and there. So with this way I can very easily redraw the plan. And finally I need a minus sign for the input value here. This line now gets an inverter, so we now have exactly this plan with C is 1, this is 0.5, this is -1, and yeah, QA comes later. So this is the typing in of a signal block diagram in my simple simulation program, and with one button you now can calculate the step response of the system. We have only one input. This should be the output. We have to note that this program calls this output number 3. This is the output number 2. This is the output number 1. Very simple. You can calculate each block output in your system. Of course, I want to see here the output of my H value. That is the output of block number 3. Okay, I click on this button, then I have a new window, the step response window. Time range should be 10 minutes. Ignore please this. We know that our time base is minutes. Normally the standard time base is always seconds. But if you want to have milliseconds or minutes or hours or so, just the program has no units. It's no problem that here you see seconds. Then you need the step input amplitude. Let's look what we have calculated. That is a QE value is 0.1, and then the units we have selected. So the input value of my step function, the amplitude is 0.1, 100 liter per minute. We want to see the output number 3, that is my level. And input is here, you see input has a number. This number comes from the program. The program looks, analyzes the circuit and looks for open inputs and numbers these open inputs starting with 71. You can have more than one input. Maybe here it could be a desired value input, and automatically if the program detects the second open input, this gets the number 72 and so on. So 71 is the number of my only open input here, and that is the point where we can just say calculate now the value of H, and we hopefully see now exactly that curve, that green curve we have expected, and you see exactly this looks like an exponential function. Final value is 0.2. After 10 minutes we reach the final value 20 centimeter drop of the system, and you see here exactly that what we have expected, and we can now do something with this, print the curve or store the curve in the internal variable, or store the curve as a text file, and later we will see what we can do with other buttons here. But this is just, you see, with some mouse clicks, with a few mouse clicks, you get step responses of this system that I want to show you here, and I think you can easily follow these instructions and redo this task in a same simple way. Okay, in the next video I introduce op amps using for easy active circuits very often used in control systems to realize filters and controllers. Yeah, that's the next video.